My name is James Lamine, and I'm a software engineer at DoorDash. At DoorDash, all of our backend code is written in Kotlin. So today, I'm going to talk about a pattern that I use for writing backend APIs. This pattern makes handling I/O easy by using structured concurrency and functional programming to keep business logic and I/O separate. The benefit is that you'll be able to respond to new product requirements without refactoring. Keep your code organized, and you'll learn how to use some cool Kotlin features. So let's take a look at the problem. Let's say that you're implementing an API which calls 3 services. The third service depends on the first 2. So we make the first 2 calls concurrently, and then call the third service. Now we have a new product requirement, and we need to get data from another service. Again, we want to maximize concurrency by calling service D as soon as we have the data that it needs from service B. The failure mode that you'll run into here is that your code will become spaghetti code. As new requirements are added, you're going to add new API calls, and you'll mix them in with the code and with the business logic in the most convenient place. As the code base grows, it becomes hard to tell which services your endpoint calls. You'll accidentally fetch the same data twice in different parts of the code, and it'll be hard to test since your business logic is mixed in with a bunch of API calls. All of this is to say that I/O is hard. For example, we might need conditional logic for deciding whether to make a request. We need to do error handling, and we want to fetch our data in parallel. From a functional programming perspective, I/O is hard because it's not a pure function. Network requests can fail, so they're not referentially transparent, which is to say that they don't always return the same output for the same input. So let's see how to solve this. In this talk, I'm going to introduce the functional core imperative shell pattern. Then I'll walk through the code for an example API, covering the basic pattern, and then I'll enhance it to show how you can use structured concurrency and lazy loading to make requests in parallel. The key idea is that we want to separate our business logic from our I/O. What do I mean by business logic? Business logic is things like deciding what data is needed, transforming the data into a response, and returning different responses depending on what errors happened. Network logic, on the other hand, has to do with fetching the data, building an object to describe what that network response looked like. Things like configuring retries and timeouts, and orchestrating concurrent requests. So how do we separate the I/O logic from the business logic? The core idea is that we want to put all of the network responses onto a single data model object. And this is key to the functional core imperative shell pattern. The outer shell of our program fetches the data model and handles all of the I/O logic. Then the functional core has all of the business logic to transform that data model into a response. At a high level, you can think of our API as a composition of 2 core functions. GetDataModel makes API calls and returns the data model. And then GetResponse transforms that data model into a response. So now let's walk through the code for a concrete example. I'm going to implement a getDeliverySummary API, which, given a delivery ID, returns some information about the delivery. Here's a protobuf defining the API contract. Basically, given a delivery ID, we want to return the delivery ID, the customer name, and the dasher name. For those of you not familiar with DoorDash, the dasher is what we call the person who delivers your food. So we can implement our API by calling 3 services. First, we'll call delivery service, and that'll return the dasher ID and the customer ID. And then we can call Dasher service to get the Dasher name and customer service to get the customer name. For now, we're not going to worry about making requests in parallel. That'll come later. So we can just call each service serially. So in this pattern, all APIs will have these 4 functions. Validate request will throw an exception if the request is invalid. For example, if a required field is missing. Get data model fetches the data model, doing all of our I/O. Get response transforms the data model into a response. And get error status transforms exceptions into the appropriate response code. So let's walk through the implementations of each of these. Validate request is simple. It throws an exception if the request doesn't have a delivery ID. I think it's best to create a custom exception class for each error that can happen. This will make the error handling easier later, as we'll be able to map each exception to the appropriate response code. The data model describes what happened during I/O, but it's agnostic about how to handle errors. So here I use Kotlin's result class to hold the response or exception for each network request. You can think of result as a union which holds either a value or an exception that happened when you were generating that value. This way, we separate the description of how to fetch data from the business logic of how to handle the response or the error. Now, let's look at the getDataModel function. It calls 3 services and saves the responses to the data model. This method shouldn't throw any exceptions. If an API call fails, we save that exception to the result object. And so we can use result.runCatching and result.mapCatching to wrap any exceptions that happened into the result. And we store the entire response from each API call onto the data model without filtering out specific fields. That's because deciding which fields you want to use is business logic, not I/O. So we just pass the entire response for each API. Next, let's implement our business logic in getResponse. Transforming the data model into a response is straightforward. We copy fields to the response using result.getterThrow to throw an exception if any of the API calls failed. The last piece is getErrorStatus, which maps an exception to the appropriate response code. These are gRPC response codes, but if this were a JSON API, you could use HTTP response codes. I recommend defining custom exception classes for each type of error that you want to handle. For example, if delivery service returns not found, we treat that differently than if it timed out. We also have separate exception classes for each API we're calling, so that we can handle errors from different services differently. By defining custom exception classes for each API call, as well as subclasses for each type of errors that those APIs can return, we have the flexibility to handle each error as we see fit and to change the error handling logic easily without changing our network fetching code. So, putting it all together, we've walked through the code for the basic pattern. Our API validates the requests, gets the data model, transforms it to a response, and maps any errors to the appropriate response code. It's worth noting that the way I'm doing error handling here is somewhat expensive. Because of the overhead of collecting a stack trace, code which throws exceptions can be an order of magnitude more slow than code without any exceptions. For my use case, this isn't an issue since the workload is I/O bound. And collecting a stack trace makes debugging easier, so it's worth it to me. But if this ends up being a bottleneck for you, then you might consider refactoring this to return the response code instead of throwing an exception. So one thing I like about this pattern is that keeping business logic and I/O separate makes it easy to respond to new product requirements. For example, what if we have a new requirement to gracefully degrade if the call to Dasher service fails? We want to set the Dasher name to null instead of failing the entire method. This is just a one-line change to the business logic. We didn't need to make any changes to the I/O code, and I've highlighted the new code in green, where I call get or null instead of get or throw. One question that people have about this pattern is, why am I using a result for each RPC call instead of a single result for the entire data model? Well, with a single result, we would have had to change the data model, get data model, and get response for this simple change in how we handle a failed API call. Let's see what that would look like. So here I've defined a data model whose fields don't use the result class. In the data model, we would change the Dasher response to be nullable. And then in get data model, we'd add error handling logic to catch any exceptions thrown by Dasher service and set the Dasher response to null. Then in get response, we would change our code to read that nullable field. So without the individual result fields, this small change to our error handling requirements ends up affecting many parts of the code. Instead, we only needed to change one line. So by keeping our business logic and I/O separate, we can respond to these new product requirements with very minimal code changes. So that's it for the basic pattern. Next, I'll add some new product requirements to help demonstrate how structured concurrency fits into this pattern. Our two new requirements are fetching data in parallel and conditionally fetching data based on some logic. So first, fetching data in parallel. Making concurrent requests can often complicate your code and make it difficult to reason about. If you need the result of one call to make another call, but those both depend on a third service, your code can get confusing. And as your business logic grows, the rules about which API calls depend on each other can also change. So relatively small features require a complete rewrite of all of your data fetching code. So how do we control which API calls to make in parallel without our code becoming a mess? We can use structured concurrency. For those not familiar, structured concurrency is a technique of arranging coroutines into a parent-child relationship. It gives us the advantages of asynchronous I/O without the readability issues of callbacks and futures. In our case, we'll chain together our API calls using coroutines. Conceptually, this makes a directed acyclic graph of coroutine dependencies. And there's no need to worry about what order to make requests in or whether they can be done in parallel. Kotlin will figure that out for us. Conceptually, you can think of it as it's traversing that graph of dependencies. So what does this look like in practice? First, we'll tweak our data model to hold a deferred result instead of just a result. In Kotlin, deferred is similar to a promise or a future in that it holds the result of a coroutine, which may or may not have completed yet. And when you call deferred.await, it returns the result of the coroutine, blocking if it hasn't completed yet. Again, the new code is highlighted in green. Next, we modify getDataModel to use coroutines. We run each API call in a coroutine using the async function. If one coroutine needs the result of another, we can chain them together by awaiting one coroutine inside the other. Here I've defined a convenience function, awaitResult, which awaits a deferred result, wrapping any coroutine exceptions that happen into that result object. Finally, we need a minor change in getResponse to await the result of the coroutine. So thanks to these changes, each API call is launched asynchronously, and requests will automatically be made in parallel. Now, let's say that the product requirements change again. DoorDash allows you to place pickup orders, where you pick your food up from the restaurant yourself, instead of having a Dasher deliver it for you. Since pickup orders don't have a Dasher, we want to skip calling Dasher service. Is this change business logic or IO? I would argue that this is business logic. It's tempting to add a quick if statement to getDataModel, but that breaks our abstraction. Deciding what the response should look like is business logic, so we should keep that in the getResponse method. But how do we do that? By the time we get to getResponse, we've already constructed the data model, and the call to Dasher service has already started. So the solution is lazy loading. Rather than starting coroutines immediately in getDataModel, we mark them as lazy. This way, Kotlin doesn't actually execute the coroutines until you call await on the deferred. So we won't make any network recalls unless our business logic actually uses or tries to access that data. To make our coroutines lazy, we pass start equals lazy to the async function. In getResponse, we add our conditional logic to only set Dasher name if it's not a pickup order. You'll notice that here I'm using launch to calculate each response field concurrently in separate coroutines. We need to compute each response field concurrently to still fetch the data in parallel. The data is lazy loaded, so the API requests don't start until you call await. But if we don't calculate each response field in a separate coroutine, it would just fetch the data serially each time we get to those await calls. So for example, when we get to the first field and call await result, that would trigger the coroutine to start. It would call delivery service and block until that call completes. Then when we get to the second field, it fetches the Dasher and blocks until that completes. And at the third field, it starts fetching the consumer and blocks until that completes. So because of this switch to lazy loading, we wouldn't be making our API calls concurrently anymore, which kind of defeats the purpose. So I solve this by computing each response field inside a separate coroutine. So Kotlin will fetch our data with maximum concurrency. Coroutines are cheap, so even if you have dozens of response fields, the overhead is minimal. And technically, you don't need to calculate each individual field inside a coroutine. If you know which fields depend on what data and what API calls, you could group them together. But this is error-prone, and the groupings can change over time. So for example, if you change where data is fetched from, or add new business logic, the groupings will change. Rather than trying to keep track of this flow of data in which you have to understand how your entire API works, I find it's easier just to compute each response field concurrently. And that guarantees that our API calls will be made with the maximum possible concurrency without me having to think about what depends on what and how that works. That's pretty much it. But one last gotcha is that you need to cancel any unstarted coroutines in a finally block. This is because a supervisor scope block doesn't exit until all of the coroutines have completed. So if you create a lazy coroutine and never start it, your program will hang infinitely. I ran into this bug while writing tests for my initial implementation, and it took some careful stepping through with the debugger and searching on Stack Overflow to figure out what was going on. The whole point of using lazy loading was that sometimes we don't want to start the coroutines. So this infinite hanging is unfortunate. Luckily, we can solve this by canceling all coroutines in a finally block after getResponse. By the time we finished getResponse, we already have done all the computations we need, so any unstarted coroutines we can just cancel. And so to do this, we have to instantiate the supervisor scope in our main API call, in our main function, and then pass that to getDataModel. Another common question is why am I using supervisor scope in getDataModel, but coroutine scope in getResponse? The main difference is how they handle failures of child coroutines. In coroutine scope, if a child coroutine fails, the entire scope fails, and all coroutines in that scope are canceled. Whereas with supervisor scope, a failure of a child doesn't affect its siblings. So getDataModel uses supervisor scope. The decision of how to handle failures is business logic, and we want to keep that business logic out of getDataModel. So we use supervisor scope because it gives us the flexibility to decide how to handle failures in getResponse by allowing each API call to fail independently. In getResponse, on the other hand, we're using coroutine scope because if calculating one response field fails, we want to fail the entire method. We're already using result to wrap all of the exceptions, so we don't actually expect any of these coroutines to fail, except for things like out-of-memory errors. So thanks to this pattern, our code is easy to understand. If you want to know at a glance what service calls your API makes, you can check the data model. And if you want to know what those services are used for, you can check accessors of the data model to see when those responses are used. Our network calls are efficient. We fetch the data in parallel and avoid unnecessary service calls through lazy loading. And by keeping our business logic and I/O separate, we're able to keep our code organized even as we add new features and respond to product changes. One last thing, this talk only covered read APIs, but you can use a similar pattern for mutation APIs. I'll leave that as an exercise for y'all if you want to try it at home. Thanks for listening to my talk. Hopefully you'll try this pattern out next time you're implementing a backend API. If you do, feel free to message me on Twitter or email me and let me know how it went. Don't forget to vote for my talk, and again, thanks for listening. Cool. And with the remaining time, I'm happy to answer any questions. Yeah.
What would you do if the data fetch of one thing depends on the result? So the parameters for fetching the data depend on the results of one other fetch.
That's a good question. Off the top of my head, I don't have an answer. What do you think? Yeah. Well, okay, wait. So like one part is you can, like because you're chaining your coroutines, right? Like I think that would just go inside of your get data model function. I think you can kind of see an example where I'm doing this already. If I pull back to, yeah. So like here, you can here the call to Dasher service like depends on data in the call to delivery service. And so I'm like awaiting the one coroutine there and then passing that ID to the next call. Yeah. Does that answer your question? Okay, cool. Yeah.
It's not very clear to me how you would structure this in a service when you have different other use cases for your application. Is it one data model per use case that is defined?
So you're saying like you have, are you saying you have a service that has like multiple APIs that you're implementing in it? Yeah, okay. Oh, cool, there's a microphone.
Okay, yeah, exactly that.
Yeah, so I would say this is like, okay. I'd say this is,
It's not very clear to me how you would structure your application if you had multiple use cases. So let's say that this service needs to grow and has other features. Say, let's get the last 10 pickup orders and then do something about it. Do you define multiple data frames in the situation, or not data frames, this is in my head, but data models, or do you do some union, or what's the strategy?
yeah, that's a good question. So I would say have a separate data model for each API that you're implementing. So if you have a service that like implements 3 APIs, you'll have a different data model for each of those. I think if you try to do too much like code sharing between the data models, it's gonna, yeah, I would advise against that.
In your gRPC error responses, I noticed you're using the with description. Is that standard gRPC or is that an extension?
I think that's standard. It's certainly standard with like the gRPC code generation library that we're using. I think we're just using the standard Java code generation. Let me pull up that code and take a look. But yeah, no, that's not like something that I wrote. Yeah, that with description is just standard like gRPC library code. And the description is like on gRPC, you can basically pass a string along with like an error code is going to have like the gRPC code and it can have like a string. So that's basically what that is.
Thank you. Second question. Have you considered using arrow at all with the either instead of result?
Yeah, I think that's a good question. I'm not personally using Arrow. Some of our code base uses it. When I implemented this, I didn't, just because I find Arrow kind of confusing. And yeah, so I don't know. It seems pretty great, but I was having trouble wrapping my head around it. If you like Arrow, you can totally use it for this. Yeah, I also wanted to avoid having to like explain Arrow stuff. But yeah, that's a good question. If anyone does end up using Arrow for this, I'd love to see your like code examples. So yeah, definitely send those to me if you do.
Thank you.
Can that also model work with reactive as well, instead of coroutines? Or
I don't know a ton about reactive programming, so I don't think I can really answer that question. I think one of the things I like about this model over reactive programming is it's it's easier to understand without needing to understand the entire reactive programming model. And so that can make it easier if you have like many different people with different levels of familiarity, like contributing to your code base.
I don't see more questions, so that's all.
Okay, thanks y'all.
Thank you for speaking.